Okay. So this is review time for the second exam. It's only on chapter 12, chemical kinetics. And if you have a chance to look at your review document, you'll understand why I'm only covering one chapter. In many respects, it's a bear. Last week, I gave you the PowerPoint lecture, and you probably learned if you've looked at the review document that just scratched the surface. That gave you the fundamentals. Once you get into the working problems, then you find out what kinetics is really about.
Will we be going over mechanisms today?
Yeah, if it's part of the document.
It is.
Okay. So, I always start off asking you if there are any particular, and you mentioned one that you want to do, which is mechanisms. But I think probably the mechanisms ought to be held till later, and we'll cover fundamentals. If you don't have any other problems that mesh with an overview, then I'll start there. Let's see. Let's start with a basic equation, or otherwise known as the rate law for a reaction. So every reaction has its own law. And that is expressed in terms of some rate, and that's equal to the rate constant times the concentration, usually of the reactant, and then to a power. So that would be the rate law for this reaction if we only had one reactant. Right, so an example would be from our lecture was N2O4 decomposition. So you would see the concentration of A decrease over time. And it would decrease based on two factors, this constant value plus its order. Right? So we've only studied zero order, first order, and second order. Those are not the only orders. And in fact, orders can be fractions. But for simplicity's sake, we're sticking to whole numbers. Now, if you have two components, you just add the other one in there with a different order. Well, it could be the same number, but it's an order with respect to that component. So if you have this reactant and that reactant producing products, then each will have its own order. So what's the total order for this reaction? It's N plus N. Simple. Okay, those are the basics for the rate law. Now, if we're dealing with just one reactant, say, and we want to characterize that reaction, we have three choices that we've studied so far: zero order, first order, second order. So for zero order, reaction, the rate law would be for a single component. That means the rate is equal to the constant. Right? the rate law doesn't care what your initial concentration is for A. It only cares what the rate constant is. Now, when this one is this is the differential form. Right? That's the differential form of the rate law. And notice with the differential form, there's no time component. What actually, well, there is a time component, but it's in this value right here, the rate. So it'll be this many units. There'll be units of concentration per time. That's your rate. But if you want time pulled out as a separate variable, you need an integrated version. And the integrated version of the zero order is a concentration at any time t is equal to that rate constant, same constant, times the elapsed time. How much time does it take to get from this one, the initial concentration, to here? This is the amount of time it takes to go from that to that. Okay, and notice that our integrated rate laws are all expressed in terms of a straight line. Right? Y equals mx plus b. So, and the other information that you can gather from the rate laws is half-life. So the half-life of the zero order reaction is what your starting concentration divided by 2 times that constant. And so this says that the half-life does depend upon your starting point. The rate law doesn't depend on your starting point, but the half-life does, which makes sense. I mean, how are you going to know how long it takes unless you know where you started from? So that's start from this point using this value, then you can find out how long it takes to lose, in this case, lose half of your reactant. Okay, so if we graph this in terms of concentration and time, what are we going to get? What do we graph? Is that the correct set of variables to graph? Time against concentration. Yeah, because this says it is. This says that if you graph A against T, you get a straight line. And notice that K is negative. That's why the slope is negative. And T is unmodified and A is unmodified. So if you graph T against A, you should get a straight line if it's zero order. Okay? Only if it's zero order. If it's not zero order, you get a curve. Right? So if you see a curve, you know that it's not zero order. Okay, the next possibility is first order. So the rate law for first order equals K times the concentration of A to the first power. Okay, so the rate law in that case does depend upon A. So how do we get a straight line out of that mess? Well, when you integrate it, the straight line is only seen if you take the natural log of A. And if you graph that one, what are the terms? What are the units for the axes? Well, t, we didn't touch t again, so t stays the same. But we transformed a into the natural log of a. So now if you plot the natural log of a against time, you'll get a straight line with that slope. And so the slope here is negative k, and the slope here is negative k. But only if you transform a into the natural log. So how would you use this? Well, suppose that you were able to plot your data like that, but you wanted to know the concentration of A at a given time, and you wanted to use your graph. Right? But it happens that the time you choose is not one of the times that's in your data set. So you go and pick a time, and you work your way up, and then you work your way over, right? Okay. So what value is that going to give you at this time? It's going to give you the log of the concentration. Okay. So if you want to know what the concentration is at that time, if it's first order, you've got to take the anti-log of that value. Okay. You don't report the log as the concentration. Okay. The only reason I'm emphasizing that is because I've seen it done, and it's wrong. So you can use this information to find out what the concentration of A is at time t. We can use the equation too. But if you want to read it off the graph, you have to transform that value into A from the log A. And then the half-life. Should be, this one is 0.693 over K. So in this case, it's kind of it's flipped. The rate law for zero order doesn't depend on concentration, whereas the half-life for the first order also doesn't depend on concentration. You want to calculate the half-life, all you need is K for the first order reaction. Let's see. I need to pick up more of that board over there. There we go. So the last one we studied was second order. Okay. So the rate is simple. I mean, if we only got one reactant with respect to A, it's A squared. Okay. Now you get a straight line out of that. If you plot either the concentration for the second order or the concentration for the first order against time, just straight data, you're going to get a curve. You're not going to get a straight line. That's why you have to do this transformation for first order. And if you get a curve with this transformation, that means it's not this one or that one. So you got to go to second order. And in this case, you take the inverse of A. I believe this is positive. Check this out. Okay. So now you have a straight line formed for the second order, and what you have to do is transform A into the inverse. And we'll go ahead and do a half-life. Yeah, 1 over. Okay. Is that right? Yeah, that's right. Okay, so for this one, if you plot the data against 1 over, which direction was the straight line go? That's positive, right? These two have negative slopes. That one has positive slopes. Then you do the same thing. If you use this graph, you say, all right, I want that time to give me this concentration. Once you get that value, you've got to take the inverse of it. Get back to this one. That's if you're using your graph. If you're using the formula, once you've got your equation with K, then you can do a calculation, and it's automatic. I mean, you just do your algebra and you solve for the current value. This is the initial value, right? 0. This is the value after time t. Okay? So those are your three possibilities for rate law with respect to one component. Okay. Let's see. So I wonder if we should do one using that scenario before we get to mechanisms. That number 1 in your review document is kind of hefty, but it does cover a lot of ground. Number 2 also. Let's do some, now, before we get in deep like that, let's do something a little simpler, like number 3. This test, number 3, is to test whether you understand really what we're talking about, what the rate law means. Okay? So let's make a little room here. I'll leave those up there for reference. So if we're going to solve number 3, the rate expression for a reaction is given as rate equals rate constant A times B squared, right? So before we get into the question, what's the order of this reaction with respect to A? First order, right? What's the order with respect to B? Second order. What's the overall order? Everybody can add, right? 1 plus 2 equals 3. Right. Okay. So the question is, if the initial concentration of B is increased from, so we're going to go with B, we're going to increase from 0.1 molar to 0.3 molar. The initial rate then will increase by what factor?
By 0.3.
Okay, wait a minute now. How did you arrive at that value?
I'm assuming because we have 0.3 right there, I think. I'll be honest, I'm kind of guessing on that.
How many times did this increase?
3 times.
From 0.1. Okay, so we're going 3 times increase in concentration. So the effect on the rate is what? 3 squared. 9 times. So you actually increase the rate 9 times because the order of B is squared. No. No, the question is, how much did the rate increase? If only this happened, change B concentration from this to this, it increased 3 times. The effect on the rate is second order, which means 3 squared. So the effect is 9 times. What if, while we're at it, what if A, at the same time as we do this with B, we increase A from 0.1 molar to 0.3. So we've increased A by 3 times, right?
12, right?
Right. Well, no, 9 increased here for this one, right? We're doing both at the same time.
Right.
So this one would give us a 9 times effect. This one would give us 3 to the first power, 3 times effect. So 3 times 9.
Oh, yeah.
We've increased, right, by 27. Okay,
What would multiply to that?
because that times that. The point of this problem is to give you another perspective of what order means. Order has an effect on the rate based on the power. That's what we're saying with that rate law. Okay. Let's see if we can step it up a notch.
I have a question that's like outside of our class.
Oh.
I got locked out of my email. I can't log into it for whatever reason. It's been the same username and password this whole time,
Yeah.
and I can't get into it. I also can't get into Blackboard. So who do I need to talk to about that?
IT.
Okay, where are they at?
At the end of this hall, on the
Yeah.
left, right before the vending machine, I guess the soda machine on the left, they're in that little cubby hole in the room.
Oh, okay, all right.
Yeah.
So I'll go talk to them after class, I guess.
Yeah. If there's nobody there, call the IT number. I think it's in your syllabus. I think I put it on the front page.
Okay. It just started, like, it was weird. I logged into it Thursday,
Uh-huh.
and then I tried to do it like Friday around 2 o'clock, and I couldn't get in. They said that it was like the wrong username and password. And I'm like, it's been the same thing since August. So, I mean, I don't know.
Yeah, it told me if I didn't change mine within a certain amount of days, it won't lock me out.
They haven't got an email about it though.
It didn't either. Every time I logged in, it just gave me a notification like, are you sure you want to just log in, or do you want to go ahead and change it? Because it depends on the days I get locked out.
I never got that though. Like when I logged in Thursday, it didn't say anything about it.
Yeah.
It just like kicked me out.
So it sounds like it's something different. Yeah, I know the message you're getting, and it's done it to me. Go get it reset.
Yeah.
I'm gonna see what I can figure out because I missed stuff for my other classes because all my classes are online.
Yeah.
So
Have you talked to your other instructors?
I have no way to talk to them. I can't email them because I can't use I don't know their email thing because the syllabus is online in Blackboard and I don't have a printer, so I can't print it out. So I have no way to talk to them about it. So
Do you know who your instructors are?
yes, but I don't know like email addresses and stuff, so I can't like email them.
If you go to the directory and type in the names, you can find their email.
Yeah, just go in the computer lab. Go in the computer lab and go to the landing page, the first landing page of New River, and go to was it faculty and staff, and then the underneath that is directory.
Okay.
Call up the directory and type in your instructor's name, and it'll give you their contact information.
Okay. All right.
Okay, so let's see. I was going to number 4, I think.
So it's E.
Yeah, 3 is E.
Okay.
Right. I added a little bit down here that's not part of the question.
Okay.
I think actually there is a question in there that addresses just what I did. That's just, saw the opportunity to do it right at this time. Okay, 4, which of the order reactions is the half-life of the reaction proportional to 1 over K? So the half-life, they're saying is proportional to 1 over K. For which of them? For 0 order, 1st order, 2nd order, or all the above, or none of the above? Well, look at the proportions. Right? We can factor out this 2 times 1 over K. Right? That's right. It's algebra. Factor out your K. This one's already got K in the denominator. Or we can say this. 1 over K. That's That's valid. How about this one? So let's see, you've got 1 over A 0 times 1 over K. That's valid, right? How do we know? Because if you multiply this times this, you get that. Multiply this times this, you get that. Multiply this, excuse me, this times that, you get that. So we know we've done it right. And proportionality is equal if you have a proportionality factor involved. So I use the proportional symbol here instead of equals. Because we can't say that T over 1/2 is equal to 1 over K. Because there are other factors involved. But we can say it's proportional to 1 over K. For 0 order, proportional to 1 over K. First order, proportional to 1 over K. Second order, proportional to 1 over K. They're all proportional to the inverse of K. Yep, all of them. So which one is it? That's D. Let's see if there are any more simple ones that kind of lead up to the more difficult. And that's too simple. Okay. 6 and 7, we're talking about mechanisms. We'll come back to that one. I'm looking for other types of problems. Okay. We might be ready to actually do a problem involving initial rates, method of initial rates. So let's do that next. Let's not do number 1 first, because it incorporates discussions of mechanism. So let's go to number 2. Number 2 would be a better choice for just looking at the method of initial rates. Okay. So I'm going to have to erase this because I need the space. Okay. So the reaction that we're concerned with is this one. Let's see, for number 2. Let me write it like this. H2C2O4. This is the manganate ion. What's this? I think that's oxalic acid. But you see those little, look like clover leaves, only they're really small. And they got little yellow flowers. Okay. You ever taste one?
Like so.
Yeah. It's sour, isn't it? It's oxalic acid. The plant is called oxalis for that reason. Well, actually, I think the acid is called oxalic acid because it comes from the oxalis plant.
So what do they use on that? Warhead stuff like the sour taste.
It's usually lactic acid. Yeah. You know, the same one that makes your muscles ache after exercising. Okay. And then CO2 plus a water. Okay. Have we done We balanced equations last semester with the half reaction method. Yeah, I thought we did. This is an example of doing it that. So if you were just given this reacts with that to produce this and that, and balance it, then you would have to split it up into half reactions. You'd have to add your protons, add your waters, and pull it back together, and then you'd end up with this balance equation. So we've conducted, or the authors have conducted, 4 initial rate experiments, 4 separate experiments. And this is the data that they get from it. So for an initial concentration of this one, 1 times 10 to the minus 3, and I don't say what it is, it's probably molar, but it really doesn't matter, not for our purposes. For this experiment, they start off with that amount. This one, that amount, and they keep that one the same for the next 3 experiments. So we have this one, this one, this one. 4 experiments. We're starting off with these concentrations of that, and we're pairing each one with the reactant here at this concentration. And notice these are initial concentrations, because this is the method of initial rates. This one they hold constant from those 2. Then they change this one to these concentrations. Okay? And then the other reactant, the last reactant, is protons. And this one has that concentration, and this concentration. Okay? And then we're given the initial rates of each one. So this reaction in molarity per second. So that's why I assume that this is in molar, because the rate is given in molarity change per second. The initial rate for this one is 10 to the minus 4. The initial rate for this one is 8 times 10 to the minus 4. 6 times 10 to the minus 3. Okay, so there's your data. Now the trick is to know which comparisons to make. So if we write the rate law, what would the rate law look like? The overall rate, which is equal to this value for each experiment, right? And the rate is also a variable. It will change depending on these factors. Whatever your K happens to be, times and then this factor, H2O4, with a different order, and then this factor. Okay, with that order. Okay, so why do we need so many experiments? The reason is the human brain isn't powerful enough to tease out answers from multi-varying experiments. What I mean by that is, if we just do one experiment, you've got these values in there, and they're present over here, but there's no way to tell what these orders are based on that information, right? Because they're all varying at the same time. So what you have to do is pair them up so that you've got factors that are held constant from one experiment to the next, and you only let one of them change. That's a key concept in doing research. The best way to get information on a natural phenomenon is to hold everything constant except for one variable. Then any changes that take place are due to that variable. So that's what we're going to do here. Which of these experiments hold two constant while letting the third vary? Well, the first two do, right? Those are constant. Those are constant between the experiments. This is the only one that varies between the two. Okay? So how do we deal with that? We ratio. We set up a ratio with, and we're going to put this one on top in the numerator and this one on the bottom. What do I mean by that? We're going to take the rate law, because we have a value for the rate for each of the experiments, and we have this variable with those held constant. So if we ratio these two experiments, putting this one in the numerator, why? Because it's the bigger one, right? It's better to have a whole number or a number greater than one than it is a fraction. It's easier to deal with. So we'll put this one on top, this one on the bottom. And we'll take that expression and we'll write this rate divided by this rate equals that expression for this rate divided by that expression for this rate. Okay? So let's say for this expression, we've got K, and we've got MNO 4 minus. Well, actually, we have values for that.
Will it be 4?
Well, yeah, that will be 4,
Okay.
right? Because these two cancel and 2 into 8 is 4. Right? That's right. Well, what's 4 equal to? 4 is equal to this one, which is 2 times 10 to the minus 3. That's 3 to its order. And then these values here, whatever they happen to be, right, are the same on the top and the bottom. Aren't they? Because we chose them that way.
Yeah.
So I don't have to write all that stuff in. They cancel. Okay? And that just leaves us with this K on the bottom, and the K's cancel. And let's see. This is going to be 1 times 10 to the minus 3 to that power. Okay? See if I still got room. Nope, I'm out of room. I have to come down the way. Okay, so now we know that this is 4, and that's equal to this expression to the power divided by this expression to the power is the same as that divided by that to the power. Correct? This is algebra. So we say this one divided by this one, and we,
2.
yeah, let me do the first one just drawn out, and then I can abbreviate on the second one. Like that. So that's equal to 2 to the n power, right? Because this cancels. So n would be what? 2, right? Square 2, and you get 4. So n is equal to 2. That means this value is equal to 2. Okay? So you just do that again, or try to find one where these two are held constant and that one varies, and ratio those. Got a picture?
Yeah.
Okay. So let's say so that gave us the n. Now we want to find out what m is. So where do we have oxalic acid varying, and the other two constant. 2 and 3. And so those are constant. Yes, 2 and 3. So we want to put this one on top and that one on the bottom. Let's see, is that true? Yeah, this is a bigger number than that one, right? 10 to the minus 3 is bigger than 10 to the minus 4. Okay, so we'll use these two. And that will put this one, 1.6 times 10 to the minus 3, divided by 8 times 10 to the minus 4. And then over here, we've got K, we've got MnO4 squared. Same thing down here, squared. Then we have this one actually does the varying. And then we got another one out here that's the same, top and bottom, so it cancels. This one cancels, and we just plug the values in for this one. Right? 2 times 10 to the minus 3, and 1 times 10 to the minus 3. Let's see, with M. Here we go. So this is what? Well, here's a way to simplify that. It is a 16 times 10 to the minus 4. Is that correct? This is the same as that. So now we can cancel these, and 8 and 16 is 2, right?
Yeah.
Okay. So now we have this one with 2 times 10 to the minus 3 over 1 times 10 to the minus 3 to the m power, which is 2 to the m power. So what's m? M is equal to 1. Okay, so now we know this one. Okay, and we just have to do the one for hydrogen. Okay, so now we just need to hold manganate and oxalic acid constant and let this one vary. So it looks like 3 and 4 would fit that bill. Right, so 3 and 4 would be the rate 1.6 times 10 to the minus 3 divided by 1.6 times 10 to the minus 3. And then this one on the bottom would be K, and then that one squared cancels. This one to the first power cancels. So now we have this one out here, which is 2 divided by 1. 2 divided by 1, and that's to the p power. Okay? So that's 1. This divided by this is 1. And then that divided by that is 2 over 1 to the p power, which is 2 to the p power. Right? So p is equal to what? 2. It is. 2 squared is 4. Any number to what power is 1?
0 power is 1.
0. So the acid component, the protons, is a 0 order factor. So now we know, there. Now we have that much. What are we missing? We're missing K. We don't have the rate constant yet. But how do we get the rate constant? The rate constant, you just, let's see. Hang on a second.
Would you need K, or would you just match up the
Oh, to answer the question, you don't need K, right? Because of the answers that you're given here, yeah. It doesn't make you calculate K.
Would be D. The answer.
D, yes. Now, why do we say that?
Because there's two of the M.
The powers match up with each other.
2 and 1.
1 is 0.
But 0 power means that one disappears, right?
Yeah.
Anything, I mean, it's 1. The hydrogen component is 1. So it disappears from the expression. If we were going to find the rate, how would we do it? Take any one of these expressions. It doesn't matter. Plug in the values for concentration and rate, solve for K. Right? So we could just take the first one. Right? So we could say the rate for the first one is 2 times 10 to the minus 4 equals K. And then that factor is 1 times 10 to the minus 3 squared. This factor is 1 times 10 to the minus 3 to the first power, and that one doesn't count, right, because it's 0 power. Then we solve these two, right? This one squared is what? 1 squared is 1, but 10 to the minus third squared is 10 to the minus 6, isn't it? So 1 times 10 to the minus 6 times 1 times 10 to the minus 3, since it's to the first power, K equals 2 times 10 to the minus 4. Okay, so this factor then becomes what? Minus 6, minus 3, minus 9. Right, you add the exponents. Here is the power, so you multiply them. But here, you're multiplying them with the product of two exponents is minus 9. So 1 times 10 to the minus 9 times K equals 2 times 10 to the minus 4. So now K is just 2 times 10 to the minus 4 divided by 1 times 10 to the minus 9, which is half times, this will be plus 9 on top, so it'll be times 10 to the 5th, right? So far, so good? Don't leave anybody behind. Bring this one up here, make it a positive, add them together, you get plus 5. This one I just did, did that wrong, didn't I? Nobody said anything.
I was going to say something. Because I was working it out.
So it's- K then is 2 times 10 to the 5th. And you just plug that in here. The rate equals 2 times 10 to the minus 5th times the concentration of manganate to the second power times the concentration of oxalate to the first power. That's it. That's your rate law. Okay. So that's method of initial rates. Now, how would I do that on a test? If I gave you that problem on a test, it would take you a minimum 20 minutes to figure it out. That's too long to test. So I would probably take a section of it, just to see if you know what you're doing.
What do you mean, just have us work out, like, instead of going through all 4 of them, you just have like 2?
Yeah, or simplify it to an equation where you only have 2.
Oh, okay, all right.
And then you only need 3 experiments to do that. You wouldn't need a 4th one. You could have a 4th one, but 3 would be all you need. Because 2 would give you a constant one with this one varying, and then you need a third one with this one coming from that varying. Okay, so let's see. Let me take a gander at number 1 and see. I would not give you one that's complicated as number 1. That is just way too much. for an exam.
Like one.
So what I would do would probably give you, I would probably focus the questions on unimolecular, bimolecular, termolecular in terms of steps in a mechanism. So how do you recognize bimolecular and termolecular? Now, let me erase this because we're going to need room for us. Let's look at some fundamentals first before we actually look at. Actually, this is not one of the problems. Maybe there is one problem like that back there. Let me check. A simpler version. Let's see if I've got some questions back there much simpler in terms of mechanisms. Okay. We'll do those after this one. No, not those. Okay. So we'll have to use, we'll use this first one, but we won't actually work out the whole problem because it will take the rest of the class period. So let's say that we've done the initial rates calculations for the number one. And what we discovered was the overall rate is this, the rate log, without calculating the K, of course, is this one for the reaction is first order, this one is first order, and this one is zero order, which the complete expression would throw that one out. But we want to talk about that one, so I'm leaving it in for now. Okay, so for mechanism one, right, so we've got this proposed mechanism is 4-step for number one, Roman numeral one. Now, Roman numeral two is a 3-step mechanism. So we're trying to decide which one satisfies. Well, first of all, what's the first condition of a proposed mechanism that is valid? The first step, I mean, the first rule it has to satisfy is you've got to be able to add the steps together and get the overall reaction. Right? And if you do that, you'll find that they both satisfy that condition. I'm just making a point, that's all. So each mechanism satisfies that first rule. The second rule is what's the rate determining step? Right? So if we look at the first one, this is Roman numeral one, this one, okay, what type of reaction is that? Well, since this is a mechanism step, all you have to do is look at the reactants. How many reactants are there? There are 2. That means this step is bimolecular. In an elementary step, in a mechanism, you look at the number of reactants, and that determines whether it's unimolecular, bimolecular, or termolecular. This is a bimolecular step. The second step, takes that intermediate and reacts it with this one to FuHOI. Right? This one is also bimolecular. Right? This one, HOI plus I plus H, yields these two products. This is termolecular. And what do we say about termoleculars? They're very, very rare. Because you've got to get these three reactants coming together with sufficient energy and orientation so that the reaction proceeds to the products. That's why the probabilistic terms, this is very rare. And then the fourth step is this one. Okay, and this is bimolecular. All right. Now, what other conditions are given here? Which mechanism and which step as the rate determining step? Okay. So if we look at the selection, mechanism 1, with the first step being the rate determining step, I think it's highly unlikely. Why? Because usually the rate determining step is the one that's least likely to occur. Right? We've got this termolecular in here, so if they're saying the first step is rate determining, I don't buy it. Although, why would I have to accept that one? If the second mechanism was just completely ludicrous, right? Then you would have to go back to that one.
The second one has two terminal.
Yes. So that makes it less likely. Plus, okay, there's another factor that has to be considered. When you're writing elementary steps, you can write the rate for that step based on the stoichiometry of the reaction. That's something that the authors may not have told you in the book, or they may have just written one sentence, and it's easy to miss. But if we write the rate for each of these steps, then this one would be like that, bimolecular. So each one of these is 1 and 1. So each of these factors is 1 and 1. And we can do that for the rest of them. If we continue through each one, well, each one of these would be written like that. So that would be 1 and 1, 1, 1 and 1, 1 and 1. And since the rate determining step they're saying is this one, then this would be related to that one. Right, so that's 1 and 1, and that one disappears, which is what this one is. Right, so if we say this is the rate determining step, we're saying that this controls the entire reaction, the rate of the reaction. And if that controls the rate of the reaction, then it should look like that, which it does. Right? We count that out. That's another reason why A is probably the best answer. B says mechanism 1, but the second step. The problem is OI minus is nowhere in there. It's not in there. So we can't determine the rate. Because neither one of these are in that expression. If we go to mechanism 2, do I want to take time to write that one up there? I want to use up all our time. Mechanism 2. All right, mechanism 2 choices say the first step is rate determining, and the first step is term molecular. Okay, that's true, but again, while it may be least probable, it doesn't look anything like this. I think that's the crux of number 1, is the mechanism 1 is preferred because the mechanism rate controlling step looks exactly like the overall reaction. Okay, that's the takeaway from this one. So if a question like this were to appear on a test, it would be simplified in terms of, actually I wouldn't put that one on the test. Don't worry about it. It's too complicated. Don't worry about number 1 as is. Think about it in terms of bimolecular, term molecular, that's a consideration, plus the rate controlling step should look like the overall rate. Yeah. Let me say that again. With all these steps, one of them controls the rate. And the one that controls the rate is the one that looks like the overall, because this is saying the rate is this. This is also saying, I didn't write that right, did I? This one is also saying the rate is equal to that. So your proposed mechanism should have at least one step in there that looks like the overall, because it is the rate controlling step. That's the takeaway from this one. Now let's look at a couple more here. Let's see. Well, number 6 is actually simplified, but it's on the same topic. So if we have step 1 is this one, and step 2 in our mechanism is this one. And this one is very slow, but this one is only slow, right? So it's relative. The slowest step is the rate determining step. Okay. So which step is rate determining? Step 1, yeah. The very slow one is the rate determining step. So that's B. The other options don't make any sense. Both steps can't determine the rate. There's always one that's slower than another. And then D, of course, that lets out 2 because it's slow. And this one's very slow. This one's slower than it is. But D says a step that is intermediate to step 1 and 2. Well, if it's intermediate, why didn't we put it up there? There's no way to answer it in terms of D, because we didn't put a choice up there. Right? We just put these 2 mechanisms. Plus, if you add those 2 mechanisms together, you get the overall reaction. Right? You get the 2 like this. This equals 2C. Right? These 2, that one disappears as an intermediate. Get one of these, you get 2 of those. So there can't be an intermediate step in there with these two reactions, because then you can't add them up to give you the overall reaction. So the intermediate is impossible. For two reasons. First, we didn't propose one. And second, if we do try to slide a second one in there, it'll screw up the total. Okay. Let's see. Let's look at this one. Number 8 and 9, actually. So we've got 8 and 9. They're based on this drawing. So we got one that goes like this, and this is, it doesn't tell you what the axes are, which means you should recognize the form. This is reaction progress, and this is energy. So we go like this, and we go like this, that, and then we got this one, there to there. Right. So that's the distance from this peak down here. And then this one goes from here to here. And this one goes from here to here. Well, that's the difference between that one and that one. And then we've got these two. This one is C. Goes from there down to here. And then we've got another one that goes like this. And it goes from here to here. Okay? So the question is, 8, which letter shows the activation energy without the use of a catalyst? So this one has no catalyst. And we want to know activation energy. Which one shows the activation energy for the reaction with no catalyst? Not even a guess. This is where you start. This is reactants. This is products. Yes. The amount of energy to go from reactants to the, let's see, there's so many different names I can put up here. I'm trying to remember the ones that we used in class. One is activated complex. So to go from here to there is the amount of energy with no catalyst. Okay? Which letter shows the activation energy with a catalyst? Yes. From here to there. And that gets you over the hump. So in that case, lead.
It threw me off because I was trying to see like the difference in between like the reactant and the product, and that was like the,
Oh, this one over here.
yeah, well, it was like I didn't see one that was just inside of like the loop up there where it like activates.
Oh,
So like it wasn't in
should be over
between, yeah. Like I
Yeah.
didn't. That's what threw me off.
Right. Okay, let's identify some other things in here. The D, for instance. D is equal to, that's the enthalpy of the reaction. That's how much energy goes into the reactants. Ultimately, reactants to products stores that amount of energy in the products. In this case, because these are lower and these are higher. Right? So that's the delta H. It's endothermic. Right? It goes in, which means we're adding energy to the system.
So if the product was lower below the reactant, then it would be exothermic.
Exothermic, right? Could be a negative number. The others are really in there just to throw you off, right? So this is saying the reactants start off at a certain amount of energy, right? They're this amount of energy, which is valid if you know where zero is, right? And zero in these reactions is really the standard state for each of the reactants. Right? So if you're reacting something like O2 and H2 in water, right? Then the starting point would be zero because O2 and H2 are in their standard states. Right? So this would really start on the axis. But if they were compounds, if you were reacting something, I don't know, hydrogen peroxide and actually just hydrogen peroxide, and it's going to yield water and oxygen. Then the H2O would have some energy in it already, and it would start up here somewhere. Then C is just the difference from the standard state conditions up to the activated complex. And I guess in some specialized situations, that might be valuable for a chemist to know, but need to know. We don't need to know it. So that was 8 and 9, plus a little extra. I think that's all you need to know about reaction progress. Let's see. I'm going to look at one other one that's not in your review document. Let me give you this one. So let's say we plot time against log, the natural log of something. And we get a straight line, and these values are going to be negative values, which is not unusual. Negative 2, negative 5, negative 1, 0, 5. So this, and you'll see that if you take your calculation, if you calculate the natural log, negative numbers are not unusual. And then let's say it takes a certain amount of time here. Say this is a really slow reaction. This is in seconds. Okay? And we're going to get a straight line that goes from 0 to about right here. As straight as I can. Like that. Okay? Now, you're given the formula for that straight line in terms of y's and x's. So you have to realize that this is equal to your x's, this is equal to your y's. That whole expression, natural log, is equal to your y's. Then we can say y equals negative 0 times 10 to the minus 5th x minus 8.87 minus 5. So where do these values fit in this table? Well, your x's going here, right? These values. Your y's are actually here. Like that. Okay? Just orient yourself. Okay. So what's the slope of this line? The slope of that line is minus 2.2 times. Yeah. That's the slope.
How you got negative 2.20.785?
It's given.
Oh, it's given.
Yes, it's given. Right. That's the formula for that straight line. Okay. So what's the order of this reaction with respect to that concentration? Okay, so we want to know what's N equal to. Can you tell?
Divide it.
You're overthinking it. How do you know the order of a reaction? What's the transformation? If the data is plotted like that, zero order. The data is plotted like this, first order. The data is plotted like this, second order. First order, right? That's the key right there. That says it's first order. What's the value of the rate constant? Okay, so look at this equation and remember that you're plotting x against y, and y is equal to log a, and x is equal to what? X is equal to pi, right? What's this one equal to? That's your starting concentration. Well, natural log of your starting concentration, that one. But what if we're asking for what's K? What is K? K is this term right there. K is the slope. Now, actually, that's negative K. That's the tricky part. If this is negative K, then what's K? K is actually 2.20 times K without the sign, because the sign just tells you that it's going this way, but the K is the positive value. You see that? This is an exercise in interpreting graphs. That's the whole point of that one. If you have that graph given to you, can you answer those questions? It's first order. What's that? And you can pull the K out of it by recognizing that this is natural log of A minus K times time minus the natural log of the initial concentration. Okay? All right, let's see. First, let me check my watch and see how we're doing. 9:20. Okay. We're good. So let's see, what else do we want to look at? Take a closer look at number 11. No, 10. Let's do 10 first. Okay, in the reaction here, we're going to decompose hydrogen peroxide. There we go. That will happen to hydrogen peroxide in the bottle on your shelf over time. right? That 3% hydrogen peroxide on your medicine cabinet will decompose into water and oxygen, right? So have you ever noticed a bottle of hydrogen peroxide that's been sitting around too long, never opened? Hopefully it's a plastic bottle. What is it? It's swollen because it's producing oxygen slowly. But over time, if the plastic is not permeable enough or there's not a little leak in there somewhere to let the oxygen out, your bottle will swell. That will happen without a catalyst. But in this case, we're proposing a mechanism in which is this produces first this, and then the second step, we take the other, right, there's one here, one there. We take the other hydrogen peroxide and react it with this intermediate to yield the other water, right, 1 and 2, plus oxygen plus iodide. Okay, this is our mechanism, two-step mechanism. So, where's the catalyst in this reaction? First of all, iodide, did you say that? Yeah. Why did you say that?
Because I'm assuming, so I'm just guessing, but where the I is on this side, and it's reacting with oxygen to make iodine oxide.
It reacts with hydrogen peroxide to produce water, and this would be the hypoiodite ion.
And then if you look in the other reaction, it's got I, but it's from that reaction, it splits off to.
Okay, right. So you've just given us the definition of a catalyst. A catalyst participates in the reaction but is not consumed by the reaction, which means it comes in one end, spits out the other end, unchanged, apparently unchanged. Okay. Okay, so this is the catalyst because it comes in here, and spits out there. What's the intermediate?
Ion?
This one.
Yeah.
Yeah, the hypoiodide.
You just said it, but I don't remember.
Right. That's the intermediate. It was produced in the reaction and it's consumed in the reaction. And for all you know, it was never there. Right? You don't see it in the overall here. Now, how do we write this reaction in terms of catalyst? Well, you just put the catalyst here. Right? That's where you stick. So that means this is a catalyst for that reaction. With that one, have the same rate as this one.
What?
With the rate of this reaction,
Without the catalyst.
right, be the same rate as that reaction. No. Which one would be faster?
The one with the catalyst.
Exactly.
Catalyst job is
Right. Now, how does it do that?
Because it's,
It causes the reaction, like it,
I know where you're going. It's just getting the words right.
yeah, I don't.
Okay. In chemical terms, the catalyst provides an alternate mechanism for the reaction with a lowered activation energy. Technical terms. Without that, you have to introduce enough energy to raise it to a point where it goes to the products. But with the catalyst, it takes less energy to get it to this point, whichever one of these. It doesn't say which is the rate determining step. But one of these is the slow step, and that's the one that you have to meet activation energy requirements. My guess is that this is the rate determining step. I'm just speculating. So with these two together, it takes less energy to get to the activated step where you go down to these products, and then when you get to these products, lickety split out the other end. So would this be homogeneous or heterogeneous catalyst? I didn't give you any phases up here, so it's kind of a guess.
I want to say hetero.
Huh? Yeah, it's homogeneous. Because this iodine is introduced in aqueous solution. This is an aqueous solution. It's really would be extremely dangerous to have pure hydrogen peroxide. So usually the highest that I've seen is 30%. You get 3% in the grocery store, but 30% if you order it from a supply house, which you can do. And then you can order iodide ion, usually as potassium iodide.
What happens if you had pure hydrogen peroxide? What does it do?
It's an extremely reactive oxidizing agent. So it'd be like, it'd be almost like dripping concentrated nitric acid on your hand. So uric acid.
So it just aids away.
Yeah, it's extremely reactive. And because the concentration is much higher, you would have more of the reactants would be activated. And they would go over to this side and produce that. And then the reaction from here to here, I'm pretty sure is exothermic, right? So you have the heat damage as well. Okay, that was 10. Now I was hitting for 11, I think. Yeah. 11. Let's see what 11 looks like. Okay. 11's going to require, I'll tell you what, if 11 were to show up on an exam, it wouldn't be exactly in this form, but it would be converted. The data would be converted. Here you have time versus concentration, right? So what you would have to do to answer the question, first order, second order, third order, zero order, first order, second order, would have to come in to play for answering one of these A through E. In order to do that, you would need to know what's the order of the reaction. So if I were to give you this on a test, I would say with this data set, I'm saying this is second order. I just come out and say that data represents second order. Right? Then you could go from there. And then if you take the A through E and say, what does A say? The decay of HO2, well, that wouldn't make any sense because it says that's first order decay. I already told you second order, so probably be a different set of questions. But I wouldn't have you, since plotting this information and doing the transformations is such time-consuming process. I'm depending on your homework to get that done for us. And on a test, what I might do I might just give you the graphs, right, and have you look at them. Say, look at those graphs. This one is the raw data, this one is log, this one is reciprocal, and you pick out the one that describes the reaction properly. Right? So it's the one that's got the straight line, correct? And then I might ask you a question about half-life. And then you would need to know that, right, for a first order reaction, say, half-life is equal to 0.693 over K. Or I might give you a data set. In fact, I think there's one in here. Let's do that. A data set relative to half-life. Yeah, 16 is a good one. It introduces using the half-life to determine K. Let's do 16. So we've got a situation where we have this one yield products, sort of a generic. And we're saying the initial concentration of this reaction is equal to 4.2 molar. Okay? The first two half-lives are 56 and 28 minutes. So what does that mean? You really can't say what it means unless you build a table. So let's build a table of A concentration against actual time. So the first one is going to be 4.2 molar, and time is what? 0, right? That's when we start. Okay. Now, the information we're given is the first half-life is 56 minutes. So after 56 minutes, how much A do we have? The second half-life is 28 minutes. But in our table, this is 28 minutes, right? What that means is the second half-life has a new starting point. The second half-life starts here. And it goes for 28 minutes. And the concentration will be half of that, right? 1.05 molar. Yeah, 1.05. But the time here is what?
56 plus 20?
Right. Says 84. Yeah, 84. Now we have our table. Calculate K. Okay. Let me be consistent. Oh, was there more information given? No. I was checking to be sure it's not based on anything above it. It's a standalone problem. Okay. So in this case, to save time in an exam situation, I might tell you what the order is. To solve the problem the way it is now, you have to plot the data, which means we have to take these values and convert them to that and this, and have values here. But if I told you that this data represents a 0 order, that reaction is 0 order. Then what you could do is say, all right, I know what T1/2 is for 0 order. this divided by that. Okay? So if that being the case, if I just tell you that it's zero order, then the calculation is simple. You could go from this data set, or you could go from this one, doesn't matter. Or you could go from both of them to check, to be sure I'm not lying to you. And to calculate K, you would say, what's the half-life for 4.2? Well, the half-life for 4.2 would be 56 minutes, would be 4.2 divided by 2 over K, and then solve for K. Okay? The other thing you could do, if I were nasty, I could say, just say, what's K? So what are your three choices? Zero order, first order, second order. So you would set up a zero order calculation, second order, and first order and second order calculation. But in that case, you would have to do this one and that one. Remember, K is a constant. So if you do the calculation as a zero order for this one, and then you set this one as your A0 and say 28 minutes, because that's your half-life. This one. So it would be 28 equals 2.1 over 2K. Then you would solve this one for K and that one for K. Are they equal? Right. If I told you it was zero order, then yeah, they would have to be equal. But if I didn't tell you, and you calculated these two Ks and they were not equal, zero order's out. Won't work. Then you do the same thing for first order with T1 half then would be 0.693 divided by K. In this case, well, in that case, you don't need the concentrations. You just calculate the half-life. Say the half-life is 56. Put 56 in here, solve for K. Then put 28 in here, solve for K, and they better be the same number. If they're not, then first order's out, and you have to go to second order. See what I'm doing? It's detective work. But if I just told you it was zero first or second order, then you could go straight to a single calculation to get K. That would be the quickest way. If I didn't tell you whether it was first, second, or zero order, you could plot the data and do the transformations, but it'd probably be simpler to go half-life route since you're given half-life. And do both half-lives, compare the Ks. Both half-lives, compare the Ks. And the one where the Ks match, that's the one. And you know that K is valid. And that type of problem will be worth more points, because it takes more work. Any questions on that one? Let's see if there's anything that I've missed covering so far that's of value. And it's 18. 18 looks like. Okay. 18, let's see, there should be useful information. All right, let me be sure it's here. Because 18 requires the use of the, shoot, I forgot my terminology. Maybe when that happens. Where's the name? There it is, Arrhenius equation. 18 requires the use of the Arrhenius equation, but not the differential version. You want to use the integrated version. So in your useful information, the integrated version of the Arrhenius equation is over here, the right-hand side, all the way at the bottom. Right. So what can you determine from the Arrhenius equation? See if I can spell this right. I think it's 2 R's. So here's the integrated version of the Arrhenius. Natural log of the product of 2 Ks. So if you got 2 different Ks, what does that mean? You change the temperature. As long as the temperature stays constant, the K is constant. Change the temperature, change the K. Why? Because there's a certain activation energy, right? And if you increase the temperature, say, you're going to increase the amount of energy available to activate the reaction. And that drives the K to a different value. So this is the integrated version of the Arrhenius equation. It's related to the activation energy and your gas constant, of course. Find that everywhere. And then these are the temperatures at which those reactions take place. Okay? Now, this is going to be the R with the joules in it, the 8.3145 joules per mole K. These are going to be temperatures. What are the units? Kelvin. They're going to be Kelvin temperature, always. How do we know that? Well, memorize it, of course. Or look at your constant. Temperatures in K. And these are going to be whatever. But unless you're solving for K, they'll cancel each other. If you're trying to find out what the activation energy is, you're going to have a K at this temperature and a K at that temperature. So these values are going to be input into your variables. That's a constant, and you'll solve for activation energy. But if you have activation energy and you run the experiment at one temperature, and then you run the experiment at a second temperature, and you want to know what the K is, it's like any algebraic expression. If all of your variables have numbers attached to them except for one, then you can solve for it. Now, let me get back to, see which one was on, 18? 18. All right. So 18, see that on the, yeah, it's showing up. So for 18, if the temperature changed to 310 K, the rate constant at K would change. So the ratio of K at 310 to K at 300 is closest to what whole number. So T1 is equal to 300, right? And T2 is equal to 310. That's not much of a change, but it is 10 degrees, right? So remember that rule of thumb? The rule of thumb says that if you change the temperature by 10 degrees Celsius, which is the same in K, the degree size is exactly the same. So a change of 10 degrees should double the rate of a reaction. Temperature change. Wait a minute. Is it basing? Maybe it's based on a. Is it coming from the problem above? I wonder. Hold on a second. We need to know what the activation energy is. Yes. So it has to come from the one above. If the activation energy, okay. So I would definitely have to give you this value. If this problem were going to stand alone, the activation energy is 98,000 joules per mole. There we go. Now with that information, we can answer the question. With 18, the way it's written, we can't answer the question. So here we've got this situation, and we've got, we want to know the ratio of K values. Right? So we want to know that ratio, K2 over K1 equals what? To the nearest whole number. Okay? So in order to do that, we need to use this expression. Right? And we just need this in our final answer. Just keep that together. You don't have to know what the individual K's are. We just want to know what the ratio is. So E sub A is the activation energy, which is 98,000 joules per mole. Looks like somebody's baking bread. Or is it just me? Some bug spray smell that way too. Did you notice that? No? That's neither here nor there. So this is 8, excuse me. 8.3145 joule per mole. K, K, big K. And these are our temperatures. So the lower temperature is 300. The higher temperature is 310. There we have our expression. Now what we do is solve for this part right here. Okay? So the inverse of that minus the inverse of that, if I did my calculations correct, is 1.75 times 10 to the minus 4 reciprocal K's. K to the minus 1. Why? Because K is down here, but when you take the reciprocal of it, you get K to the minus 1. Okay? Just saying. And this value reduces to 1.179 times 10 to the 4th K, because that cancels, and K is in the denominator of the denominator, which means it's in the numerator. Right? So when you bring this up here, you flip it. Right? Flip it like that, that puts K up here in the numerator. So this K times this K to the minus 1 cancels. Right? It's like K divided by K. Right? So now you have a dimensionless number, which is what you should have, because these dimensions cancel those dimensions. Right? So we're just doing a reality check here. So this one times this one is what? Here we go. So this one times that one, and then this one is 10 to the 4th, and that was 10 to the minus 4th. So that one reduces to 1.2675 is equal to the log of our ratio. So to find the ratio, you need to take the anti-log of that number. Everybody know how to do the anti-log? The anti-natural log. It's e to the x on your calculator. Right? You may have the LN key and then the function. The function key above it should be e to the x. So just, this is your x value. So e to that value is this value. So K2 over K1 e Let me see.
It gave me, I think I did it right. It gave me 2.37 times 10 to the minus 1. I rounded.
675.
We do each that value 1.26.
Yes, and I get
I got
3.55.
3.55.
Okay? So that's the actual ratio of K2 to K1 with the reaction of this activation energy when you change the temperature from 300 to 310. Right? So the nearest whole number is what? Right. So we're saying that when you change the temperature by 10 degrees in this range, with that activation energy, you actually quadruple the reaction rate. Questions? What's the key to this problem?
I do have a question. I don't know
Yep.
if I missed it. So where did the 98,000 come from?
From the problem above it.
Oh, that's why. Okay.
That's what I was saying before. 18 won't stand alone as written in your review document. So if it were to appear on an exam, I'd have to give you that value. There's no other way. Because if you don't have this value, then you've got an equation and two unknowns, and you can't solve it. But if we know this value, these two values, then we can find out what that ratio is. Let's see, is there anything else that just kind of jumps out at me, or you, for that matter? About 20. I think 20 should be fairly easy to solve. It uses half-lives. Chemical half-lives, that is, not radioactive half-life. Although the concept is similar. Let's see. So the first order decomposition of hydrogen peroxide at minus 30 degrees. First order decomposition. So it's going to this and this. I think that balances it. And the temperature is minus 30 degrees C. Has a half-life of 42 seconds. 42.0 seconds. What will be the residual concentration of the if we start off at this concentration, 0, of 10.2 molar, and the elapsed time is 3 minutes. Okay. So since this is in seconds, I think it'd be simpler to convert this one to seconds. This is equal to 180 seconds. Okay. So that's the given information. Now we've got to find out what's left over after 3 minutes. Oh, what else? We also said first order. So this reaction is equals that first order. That's given also. So that means this half-life is equal to what? What formula? 693, right? Divided by K. There we go. All right. So, since it doesn't depend on concentration, we can go ahead and calculate what K is, can't we? We say K is equal to divided by 42 seconds. Okay. So we know what K is in a second. 1.65 times 10 to the minus 2 seconds to the minus 1. That's K. So let's see, what's my next step? We need a formula that's going to incorporate time into it and concentration. So we need the integrated version of the rate law. This won't tell us anything because that's our starting point, and we know the K, and all we can tell from this is the rate. So what we need is first order, right? H2O2 equals minus KT plus this one, oops, generic, real thing. There we go. Okay. So we've got the K right here. We got the amount of time elapsed, 180 seconds. We got the initial concentration, which is 10.2. Okay, 10.2 there. 180 seconds. We got the K. Right? So we can solve for the actual concentration. Yeah. So we set it up like this. That minus the K, 2, and the time. I left out the seconds because this second cancels that second, so we don't need it. And then the natural log of 10.2. There we go. Everybody okay with the setup? Okay. So this one, sure. Yeah. That's right. This is going to be a negative number, right? So if I did my math right,
What do you,
is that right? Is that what you get?
I got negative 6.40.
Here?
Yeah. Let's see, I'm doing that in science notation too. But
Let me recalculate because I can't make mistakes.
What you get, Zach? I got negative 2.97.
if I don't put in science, it gives me a negative 0.64.
Did you do all of it or just that first part?
This is negative 2.97.
I did it all.
Oh, okay. Okay.
He's only doing the first two. 1.65 times 10 is like
Oh.
It's always doing.
Oh, okay.
He didn't put the natural log in there.
And then the natural log of this one is 2.332. Right? So those two together, oops, that's wrong. Forgot the sign. There we go. So this is negative 0.65 is equal to the log of that value. So we just need to take e to that power. Right? And that says that after 180 seconds, we started out with this concentration, and now the concentration is equal to 0.5. Close enough. Rounding error.
You have to take e to the.
Oh, okay.
Power.
E to the negative 0.65. So for a first order reaction after 3 minutes, you've lost quite a bit. If it were zero order, this would be a lot higher. You would lose less. Second order, you'd lose even more. And we did 3 of those comparisons in our PowerPoint slides, just saying, what if it was zero order, first order, second order, based on the rate law that was given. We just changed the orders. Then you see that zero order leaves more, first order leaves less, second order leaves even less. Okay. So, does anybody have any comments, questions? Sure. Oh, on this one? Yeah.
Where did the 180 say? I keep trying to find out how you got 180 seconds.
Right here. T is 3 minutes. 3 times 60 is 180.
Oh, that's it.
Okay.
Okay, wait.
I did a flyby on that. Your question?
No, I figured out how you go. There's 0.522.
Yeah. So this is e to the minus 6. Oops. 0.6. Okay. So let me see. The test is going to have 77 points and 20 points bonus. But all the questions are multiple points. There's nothing less than 3 points. So that's why 77. It just sounds like a lot, but it's really not.
And there's bonuses.
And they're bonuses, yes.
That you got to show your work.
Yeah, I appreciate it. Okay, let me stick this back in here. And then we can look at the lab. Does anybody need to take a break before we talk about the lab today?
We're working on figuring out the questions first.
Yeah, we'll get those in. Were y'all absent?
Yeah.
You know those things are online. They're on the Blackboard. That way you can come to class prepared. And that, you don't need that right away because that's helping with calculations.
This hydrogen.
This is also.
I thought I lost it. I don't know if that whole stuff. I think it's something that the calculations or something.
Okay, chemical kinetics lab. Different version. There's my version. Too many copies of stuff. I might have to do it on the fly. I think I can do that. Just want to be sure I'm in the pre-lab questions, when I do this. Pre-lab, here we go. Is it? Yeah, okay, it has the wording there, that's good. Okay. So let's make some room here.
Did we work on pre-aligned questions today? Did we put that in our live report or?
Let me see what's involved here. You're gonna have to do that again anyway. No, you don't have to do those. Just the post-lab. In fact, the post-lab questions are going to be embedded in your results, calculations and results. So for the post-labs, all you have to do is, I think for most of them anyway, you have to just list the number and say refer to.
Yeah.
Some are like, some post-lab questions are standalone for some labs. And then others, they tend to double back into the report. Okay, so pre-lab. Let me, this is our second lab?
Yeah.
Yeah.
Lab 2, for the benefit of our viewing audience. Pre-lab cues. Okay, for the first one. A container of household bleach has 5% sodium hypochlorite. That's what that OCl is, the polyatomic ion, hypochlorite. Remember our polyatomic ions. If you start from here, then you can add one, and then you can take one away, and you can take another one away.
Yeah.
Right? So this is chlorate, this is chlorite, this is hypochlorite. So all they've done is they've just turned it around for sodium hypochlorite. Because sodium comes first, then we want the negative side opposed to the positive. That's the only reason it's written that way. So the sodium hypochlorite solution is 5%, which means what? Percent means nothing. It's a dimensionless number. Unless you're told what it means or given clues. And the clue here is the density. Right? The density of that solution is 1.08 grams per milliliter, mass per volume. So that means this should be mass per volume. Okay? Otherwise, they wouldn't give you that. And that's usually what percent means, whether it's bleach or vinegar is 5% acetic acid, it's mass per volume. That's the problem with percent. They got to tell you what it is. Okay, so that information is given. Calculate the molarity. So we want to know the molarity of bleach. Actually, not bleach, because bleach is a diluted version. The molarity of sodium hypochlorite in that solution. Now, why do we need to know that? First of all, otherwise this is just an exercise in futility. We need to know the molarity of the bleach for two reasons. First of all, when we're going to conduct the experiment, we need to know the concentration of the component that goes in, right? Because the reaction is the rate law ultimately is this, our K times the concentration of the dye. And one group will have blue dye and one group will have red dye. Dye to some order times the concentration of the bleach. Well, actually, I should be more consistent there. Sodium hypochlorite to its order. Okay? So if we're going to write this correctly, we need to know the concentration of the bleach in the reaction solution. And the first step in that is knowing what's the concentration in the stock before you dilute it. So in order to find the molarity, which is our target, we're going to need to know, since this is in terms of what? Moles per volume. We're going to have to know the moles of sodium hypochlorite. In other words, we need the molar mass. We know we're going to need that. So we get to say sodium is 23.003.
16.
Remember that one? 40, 35, 49. Now we can add those together. That's 14. And 1, 7. Okay. Hold that in reserve. We'll need it in a minute. Okay, so now it's really just an exercise in conversions. So you need conversion factors. So what does 5% mean? 5% means, and this, let's see, does it give us, yeah, it does give us decimals. So we have 2. Is percent is parts per 100. And that's a little tricky with mass volume. So what you have to, we have to actually assume that the mass of a milliliter of solution is the same as water. It's 1 gram is 1 milliliter. So it'd be grams per 100 milliliters. That's what that means, grams per 100 milliliters. Big mass volume, right? Parts per 100. But in order to do that, you have to assume that the mass of 1 gram is the same as 1 milliliter. So there's your first big assumption. So this is so many grams of sodium hypochlorite per 100 milliliters. That's our starting point. And we need to end up with moles per volume. In order to do that, when you have 2 units that are going to be changed, you do 1 unit at a time. Remember? So the grams, we need moles. Right? So grams on the bottom, moles on the top. And now we use this number, 74.45. Like that. That gets rid of grams. Now we got moles. We're good. Moles of sodium hypochlorite. Wait just a second. Do we need the density? Oh, okay. Hold everything. Dick Tracy called them headquarters. What they're saying is that it's not mass volume. Mass. Okay. Does that confuse anybody yet?
Why is it mass?
Because they gave us density.
Density is mass per volume.
I know. But if you've already got volume, you don't need density. It just dawned on me. If I have mass and volume here, what that assumption I was making, 1 gram per milliliter is wrong, because it's 1.08 grams per milliliter.
So we look for the math.
We're going to convert mass to volume. So it's 100 grams of solution. Will give you 5 grams of sodium hypochlorite. Okay? We've already converted now to moles. That's good. But now we have to convert this to volume. So we've got 1.08 grams per 1 milliliter. So that gets rid of these grams here, these grams, and these are milliliters. Now we got volume, but we have the wrong volume. We need liters, right? Because this is moles, and this is liters. So this has to be converted to liters. Now that should give us moles per liter. And it's just crunching numbers at this point. I apologize for that. It'll spin your head around. 74.45. 8,000. So I get, what do you get? I'm gonna wait. Right? This and that and that and that. Divided by this, divided by that, divided by that, divided by that.
7.25 times 10 to the negative 1.
Right. And we started off with 3 significant figures. So we can keep 3 significant figures. 0.725 molar. So I was wrong. The authors are saying that 5% sodium hypochlorite is actually mass-mass ratio, whereas vinegar is mass per volume. Okay, so that's number 1. Now, when you do these calculations for the lab, we're not using 5% sodium hypochlorite. We're using 6%. Right? So what would you do there? Just use 6 here, plus 6% is more concentrated sodium hypochlorite, so the density is probably going to be different. And if you look in the you look in the method, and it'll tell you the density is 1.09. Okay. So you just substitute 6 here and 109 here and get your answer. In fact, I've already done it for you, and I've already prepared. This is the second reason we need to know that concentration. Because the first experiment is with full strength.
So like on activity 1, where it says density bleach, we put 1.9.
It should be in there.
Yeah, that's right.
So we're going to do the first experiment, full strength bleach. Then we're going to run it through again, half strength. Okay, full strength, you just put your dye solution and the amount of bleach that you determine in the process, how much bleach you need to decolor the dye in a certain period of time. Right? The method tells you that. Then you use half that much, right? But you want the concentration to be half not just the amount you add. So you got to make up the difference in volume, right? If you're only, say you, it requires you to add 40 drops of bleach to get the full strength reaction. Then you would use 20 drops for the half strength, right? But what happened to the other 20 drops? You've got to make up the difference, right? So, do we make up the difference with water? No, because we have bleach that dissociates into those two ions, which means the solution is at a certain ionic strength. The concentration of ions is a certain level. You have to maintain that level in order for the reaction to proceed with the same mechanism as with the full strength. So what the difference you make up there, this is the business end of the molecule. That's the one that causes the decolorization, not this one. So instead of this, we're going to substitute this. Now, that will not decolorize. This will. But it maintains the ionic strength because you got one cation, one anion, one cation, one anion. So we make up those 20 other drops with a solution of sodium chloride that is the same strength as bleach. That's why you calculate, and your number is going to come out like 0.8 something. So we make up a sodium chloride solution, which I've already done for you. And when you put 20 drops of bleach in there, you make up the difference here with 20 drops of sodium chloride. So you maintain the ionic strength of your solution. That means the reaction, the only thing changed in the reaction is this. Right? Remember I was talking before, you don't want to change more than one factor at a time. Otherwise you don't know what's responsible for the change. Yeah. So we make this constant with that. And then we know that this is responsible for the reaction in both cases. Okay? So you'll have to calculate that. I'd advise you to do it using 6 here and 1.09 there, see what you get. And then when you go in the lab, you can pick up the bottle of sodium chloride and see if I got the right concentration. That matches your value. Okay, so that's one.
So do we find is where I've been reading on some of this recently?
Yeah.
Is the mass of bleach like the per drop? Is that in our lab activity?
The mass of bleach per drop?
Yeah.
Oh, okay. Okay, here's what you have to do to find that.
Okay. Because we got the density, it's just.
If you've got a 6% solution of bleach, that means 6 grams per 100 grams. And you want to know how many grams is in each drop.
Yeah.
Right? So what you do is you just pick an arbitrary number, like maybe 50 drops. You can go 100 drops. And you tear out a whey boat. Right? The whey boat is resistant to bleach. It won't hurt it. Make it 0. Put your boat on there, make it 0. And then you just drop 50 drops. And it tells you your mass.
Oh, okay.
So that's the mass of 50 drops. Divide that by 50 and you got a mass per drop. So the reason you want that is because if you add 40 drops of bleach, full strength, then that translates into 40 drops. 40 drops translates into a mass. Because you can multiply that times the weight of each drop. And you get a total mass of bleach that was added to the solution. Your chore today is to get the data.
Okay.
And then the calculations will come. And that's why I gave you those extra pages to show you how those calculations were done. All right, let's get the rest of these pre-labs out of the way. Let's see. Is this a pre? Yeah, it's a pre. So this is a pre. Number 2. Actually, before I do number 2, I want to make a comment on the procedure. When you determine, you're going to use test tubes to determine how many drops you need to add to a certain volume of bleach to color it. So you need to determine what's the volume of dye that goes in the tube. Say it's, just for argument's sake, 5 milliliters. Right, so many drops per 5 milliliters of dye. Drops of bleach per 5 milliliters. But your cuvettes are not going to be 5 milliliters. Right, your cuvettes may be 2 milliliters. The cuvettes are going to be these little things like that, and they're like this. And the light beam is going to be shining through. Here, like that. So you want your liquid to be up to a certain level so that the light beam can shine through there. And as it decolors, as the reaction proceeds, you're going to see the absorbance go down, 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 down. So you're measuring the concentration of your dye as absorbance units, which is okay. So the reaction itself takes place like that. It starts fast. It takes seconds, like you're going to measure over a period of minutes. But the beginning of it starts really quick. So what you want to do is put your dye in here and then stick it in the colorimeter or the spectrophotometer and add your bleach after it's in there, right? Because it's going to start right away. So what you need to do is once you've determined how many drops per 5 mils, then you find out, just take a cuvette and add water in it up to a certain level, and then pour it in your 10 mil volumetric and find out what that volume is, right? And if it's not exactly like 2 mils, but say it's maybe 2.5 mils, then you could back it down 2 mils. If you say 2.5, then you'd need half the number of drops, right? So you fill this up with your dye, exactly 2 mils or 2.5 mils. Make it 2 mils, because I have a 2 mil pipette. But you want to know that exactly. Then you add the number of drops of bleach based on this ratio, right? If you only use 2/5 of that volume, and you say you need 40 drops in 5, then you need, what's 5 in it? 16. Then you need 16 drops in here to give you the same ratio, right? Because if you do the mixing in a tube and then you pour it into your cuvette, the reaction's halfway done by the time you get started. Right? So that little change in the method is necessary to get good data. Okay, Now let's go back to question 2. How many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? Okay, so what was the concentration from question 1? Remember?
0.725 molar.
Molar, right. So that's molar. This is the concentration of the 5% bleach, but we want to make an equivalent concentration of sodium chloride so that we can match that in the half strength. We can use that to make up the difference. So we need to know this value. And this is also a calculation. Well, actually, I did this calculation and made the solution already. Right? So you don't have to do another one like this for current. Solution's already made. But in this case, if you were going to make up a solution of sodium chloride to match that concentration, how would you do it? Well, this molarity is moles per liter. And the question is, how many grams per liter do you need? Right? So if we got moles per liter, we're going to convert it to how many grams per liter. So what do we need? Whenever you see grams and moles in a quotient, molar mass. So what's the molar mass of sodium chloride?
Isn't it 74, 45? Oh wait, no, 74.
Mm-hmm. No, this molecule is different because we don't have an oxygen in it now. And the chlorine is 35.
23 plus 35.45.
Right. 45, 8, 5, 58, 45. There we go. So multiply those two together, and you need 42.4 grams of sodium chloride per liter of solution. Who's going to make a liter of that stuff? You don't need a liter. We need drops, right? That answers the question, though. But how many grams would you need if, say you only needed 100 mils? Well, let's say 250 mils. If that's the ratio in a liter, and we only need 250 milliliters, right? If we put milliliters there, we can't cancel the liters. But if we put liters there, 250 milliliters is 0.25 liters. Then we just need a quarter of this, right? So what is that? Let's see, 4 is 1, and 4 and 2, 0. It's 6. So if we put that much in a half a liter of solution, we get the same concentration. Okay. 250 milliliters. We're going to make it, instead of making up a liter, this answers the question. That's the answer to the question. I'm just extending. I don't want to make up a liter. I want to make up a quarter of a liter. And we have volumetric flasks that are calibrated for 250 milliliters. That's why I chose that. We also have 200 milliliter ones. We have 500s and we have 100s. But say I want to make up 250 so it'll last me for, say, 5 years of student labs. Then I've got enough to go from year to year to year. You just have to be sure that you keep it tight, the cap, so it doesn't evaporate. The sodium chloride is not going to degrade, but the solution could evaporate and change your concentration. So you want the cap tight between student labs. Okay, so that's 2. And we had a 3, didn't we? Yeah, there's a 3. Number 3, pre-lab. What's the percent of sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite and has a density of 1.09 grams per mil? Okay. So we're given this concentration, molar sodium hypochlorite, okay, and we're given its density is 1.09 grams per milliliter. And the question is, what's the percent by weight? This is percent weight, and be consistent, mass. That's the question. So we're going to want to know grams of sodium hypochlorite per 100 grams of solution. Okay, so this is our starting point. And this is moles of sodium hypochlorite per liter of solution. So we want to end up with grams per 100 grams. So to convert grams of this, we need your value, 70 something, right?
Isn't it
74.45.
Yeah, 74.45. Okay. Now we've got grams of sodium hypochlorite. Now we need 100 grams of solution. Well, this is liters, so we're going to need milliliters. Right? Because the density is in terms of milliliters. Right? That's 1.09 grams per milliliter. But we want to know per 100 grams of solution. See what I did there? We're going to keep this whole thing here, and we're going to throw that one in there as part of the calculation and keep this, because 100 grams per 100 grams on the bottom gives us percent. And we want to get rid of that 100 on the top. The other way to think of it is, all right, so if this is grams per gram of solution, then multiply it by 100, and that gives you percent. This is how percent works. Right? It always says something divided by something times 100 gives you percent. The reason it's times 100 is because of this factor. That's equal to 1. But we're going to keep this whole because it's per 100. But we're going to multiply it by 100. Right? Remember when we were doing percent composition? Because the mass of the element per mass compound times 100. The reason we multiply it by 100 is because of that factor. We just never explicitly said it. All right, so the calculation then is 0.8 times 74.45 divided by 1,000 divided by 1.09 times 100.
You give me 0.05. It's fair because I'm rounding it to
I got 54.6 for it.
You're off by 1 decimal. Let me calculate to be sure I'm having
Like I
it.
said, let's say I rounded up.
0.8 times 74.45 times 100, right? Divided by 1,000, divided by 1.09. And I get 5. See, we got 3 significant figures, 5.46%. Mass. Okay. Wondering what you did wrong?
Well, I did get 5.46422 times 10 first round.
There you go. And this is the controlling significant figures. We have 3.
So why do we not change it to 54.6 to take it away the end of the first?
Oh, yeah. That's valid. That's scientific notation. Yeah. Okay, so that's all of our pre-lab questions, right?
Yeah.
All right. How we doing on time? Is it time to go in the lab yet?
It's 10:44.
Okay. So I've got 2. Oh, one other thing I didn't talk about. Absorbance. We're going to be measuring absorbance values for our color, our dye. Right? It turns out is absorbance is proportional to let's write it this way. A, B, C. So I have to tell you what the A, B, and C mean. Okay. C is concentration. So as concentration increases, absorbance increases. That's why as the concentration decreases, the absorbance will decrease. And it's a linear response. Right? So as the concentration changes, it changes linearly with absorbance. B is the path length of your cell. But that's not going to change. Right? You stick one cell in there, stays the same. So this doesn't change at all. Right? A is specific absorptivity. And this value is characteristic of every chromophore. What do I mean by chromophore? Chromophore just means colored body. That's what produces the color in the dye. Right? So it has a specific absorptivity, that is, for a certain amount, it will absorb light at this much, at a given wavelength. Right? This doesn't change either. Because once you put it in that cuvette, you don't put anything else in there with it, right? So these two are constant. This is the only one that changes. That's why we're going to relate that one to this one. So we don't actually measure the concentration of the dye. We substitute absorbance for the dye concentration, okay? This is known as Beer's law. And sometimes we give credit to Lambert too.
Yeah, it said that on the
Beer-Lambert law. Yeah. And it just says, as the concentration increases, absorbance increases, like that. Okay? So if we need to take a short break, we'll meet up in the lab. And I'll show you where everything is.